Go ahead, Tom. Make them.
Can you hear me okay?
Yeah, I can.
Okay, great. So I enjoyed the discussion, previous discussion, especially the part about dust on Vesta. And I would just say, to start out with, that Vesta probably doesn't contain a lot of carbon, unless, of course, it's chocolate Vesta. And so we don't expect to see much there. So let's move on and talk about Ceres. I'm going to talk about carbon on Ceres and a little bit about what constraints we have from Dawn's gamma ray and neutron detector. But first, I'm going to start about what we know about Ceres surface composition. Namely, we know that hydrated minerals are pervasive on Ceres, and we believe that these minerals form by the action of liquid water within the interior. And we also think that Ceres has experienced a high degree of aqueous alteration. And these alteration assemblages contain magnesium phyllosilicates, ammoniated clays, carbonates, and a darkening agent. And the plots on the right show on the top the ammonium band measured by Veer at Ceres and the OH band below. And these show a lot of contrast, but the scale is stretched. And if you take the top map and smooth it to the resolution, the very broad resolution of Dawn's gamma ray and neutron detector, you'll see that the dynamic range for the Veer data is very low. And so what you're seeing is a surface that's fairly homogeneous, and it's covered with these phyllosilicates. And what the GRAND data initially provided for us was a view beneath the optical surface within the top few decimeters. And you can see the GRAND plot of water equivalent hydrogen below the Veer map of ammonium. And you can see its dynamic range is something like 60%. And the range of water equivalent hydrogen on Ceres goes from about 16% near the equator to 29% near the poles. And we take that as evidence for a broad global subsurface ice table, which is anticipated from ice stability models. So what about carbon? Carbon on Ceres, we know from spectroscopy, is in the form of carbonates. The global surface contains magnesium carbonates. The bright spots contain sodium carbonates, and there might be ammonium salts present. In addition, organics are localized to just one place on Ceres. You have aliphatic organics in and around Vernitech crater. There's also evidence, as Amanda pointed out earlier, for graphitized carbon on the global surface, which we'll talk about in a minute or two. From the Veer data, we can get constraints on how much carbon, how much elemental carbon might be there, just based on mixing models. And the mixing models imply a minimum of about 1 weight percent carbon on the surface of Ceres in the form of carbonates. And you'll see in a moment that GRAND measurements permit higher carbon concentrations. So before I get to the GRAND measurements, we may as well say something about Ceres analog materials. These are the aqueously altered carbonaceous chondrites. On the plot to the right shows carbon in weight percent and hydrogen in weight percent water equivalent for these materials. And in them, carbon is partitioned into organics, carbonates, and some unidentified components. But if you look at the plot, in green, I'm showing the organic part, and in purple, I'm showing the carbonates. These meteorites mostly contain organic species. So carbon is primarily in the form of IOM. So cometary materials, which we use in our simulations and we don't necessarily regard as being a Ceres analog, may contain much higher concentrations of carbon than shown here. Peak for the chondrites is about 4 weight percent. So what do we see with GRAND? So elemental measurements by GRAND, these are cosmogenic neutron and gamma ray measurements. So you have a galactic cosmic ray that comes into the surface, breaks apart nuclei, and you produce secondary neutrons. These secondary neutrons rattle around on the surface, colliding with elements that are there and escape into space where they can be detected. And along the way, they make gamma rays. And the gamma rays provide a fingerprint of the elemental composition of the surface. So what we had the opportunity to do with Dawn, which is really cool, was to compare Vesta and Ceres. Vesta, unless it's chocolate Vesta, has a lot, does not have much carbon, and we get a gamma ray spectrum that looks like this. This is the high energy portion of the gamma ray spectrum above 4 MeV. You can see reaction peaks from neutrons on iron, on oxygen, and on carbon, and they mix together to form the spectrum. One of the things that we can do is we can strip out contributions to the 6.1 MeV peak shown here, and that leaves us oxygen contributions. Those are shown in purple. And we can use those oxygen contributions to estimate how much oxygen we would see in a peak that contains contributions only from carbon and oxygen at 4.4 MeV. When we do the same thing at Ceres, we find that oxygen contributions go down, yet the carbon 4.4 peak hangs in there. And the residual is likely due to carbon in Ceres surface. And so from the gamma ray spectrum, we have the statement that carbon is present in Ceres regolith. We still have a bit of work to do to quantify carbon. It's actually a very challenging problem, but we at least have some information to suggest that we might have elevated carbon in Ceres. The next bit of information we have is from neutrons. And on the right, you're looking at the neutron leakage spectrum. So you've got neutrons as a function of kinetic energy. And neutrons are made by these spallation reactions. They slow down by successive collisions in the regolith until they get to thermal energies. The spectrum that you get in the epithermal range for neutrons that are slowing down from production to thermalization is approximated nicely by the Fermi approximation. And basically, we find that the flux of neutrons slowing down is a balance between production S and the energy loss cross-section. Energy loss is high for moderating materials, light elements like hydrogen, to some degree carbon, but overall, what we see in the spectrum is a balance between production and moderation. We use fairly complicated simulations to sort out for analog materials what the fluxes that we measure look like. And on the left, all I'm showing is that if you add carbon, which is a fairly light element, for analog materials for Ceres, the energy loss cross-section actually increases. So you expect a suppression in epithermal and fast neutron fluxes. However, at the same time, as you add carbon to these materials, you decrease iron, and you decrease the effective atomic mass, and therefore you decrease production. And that's another way in which fast neutrons or epithermal neutrons would decrease. So we have to turn to our models, and on the right we have a plot of thermal plus epithermal counts simulated for GRAND versus fast neutron counts. And therefore, two N-member materials, CI chondrite and Halley's dust. And what you'll see in a moment is that if I take actual data from GRAND and plop it onto this chart, you see that Ceres plots between these two N members. So the takeaway from this is that GRAND neutron measurements permit high concentrations of carbon in the subsurface, and that Ceres plots between the carbon-rich N members, and that the data are more consistent with cometary dust than with the CI chondrites. So another way that we can look at carbon is to imagine that carbon might be mixed in with the feed materials that made Ceres, and we think that these would be very much like the CI chondrites. And the plots to the left show hydrogen and iron concentrations across the surface of Ceres, and on the right you have a plot of iron versus hydrogen. And I've put the CI chondrites on this chart, and I've also added a line where I'm adding and removing water from CI. And so we have a dilution trend that we want to look at. And what I'm going to do next is I'm going to compare the concentrations of iron and hydrogen in Ceres equatorial surface, where we think water ice is not present, at least not at the depth sensed by GRAND, and see where Ceres falls relative to the CI chondrites. And if I do this, you can see that Ceres has more hydrogen and less iron rather than the CI chondrites. I can further plot the high latitude points on Ceres, and I find that the iron hydrogen trend follows a water dilution trend, although shifted from the CI trend. So why is it that the CIs and Ceres are different? And one approach might be to model the addition of carbonaceous material to CI. And so that's one of the things that we've done. So it turns out that you can actually match the equatorial data cloud for a Ceres by adding in IOM and IOM mixed with carbonates. And the mass fraction of hydrogen in the added material simply determines the slope of the mixing trend. For water, we get 11 weight percent hydrogen, and we've already discussed that the dilution trend does not match the data cloud. So we need something with a little less hydrogen in it. Here's IOM. If we just take a Murchison polymer containing carbon, hydrogen, oxygen, and nitrogen, and add it in to the CIs, we do intersect the data cloud very nicely. If we add carbonates, we can actually bound the data cloud from below. So it's certainly reasonable that you can mix what we believe to be the feed material for Ceres, which would be like the CI chondrites, with some carbon-rich material and match the equatorial data that we see on Ceres. So there are a variety of other possible things that you could add in to do this, not a unique solution. You could certainly add in ammoniated salts, but bound or interlayer water would not work. So the bottom line is that the data are certainly consistent of some combination of organics, carbonates, and salt hydrates being added to the solar nebula composition to explain Ceres' equatorial surface. And we can make a plot then of our inferred range of carbon and measured hydrogen and compare that to the meteorites and also dust from Comet Halley. And we can see that the elemental measurements are certainly consistent with Ceres having a surface that's carbon rich, in fact, that has superchondritic concentrations of carbon. Now, this might be in the form of organics. If it was, then the reason we are not seeing it might be because of ionization and destruction of the IOM or the organics by UV or ionizing radiation. So the superchondritic concentrations of carbon, because we think that Ceres feed material would be represented by the CI chondrite, is really consistent with the idea that Ceres has a differentiated interior, and there are lines of evidence that indicate that Ceres is both physically and chemically differentiated. And certainly, if this were the case, the presence of carbon in an aqueous environment would certainly make Ceres an attractive and accessible target for studies of prebiotic chemistry. So I'll leave you with the idea that we're going to find out more about chemical composition of Ceres surface starting in June, when our low altitude mapping orbits commence, and hopefully we'll have a lot more to say about what's there later. Thanks for your attention.
Thank you.
Great, thank you.
Questions for Tom? Verbal? Somebody is typing. How much carbon does the chocolate Vesta have?
I don't know. I have a neutron spectrometer. I should try and figure it out.
Okay. Just checking.
Okay, what is chocolate Vesta? I don't know what we're talking about here.
Ha ha ha.
Oh,
go ahead, Tom.
There it is. Chocolate Vesta. You may not be able to see it because our Wi-Fi is not good, but it's a 3D printed model of Vesta. Rendered in chocolate. Okay. What will the spatial resolution be? I think Oh, there are two questions. I can barely read my screen, so if somebody else could read them to me, that would be great.
Sure, just a minute, let me see. What will the spatial resolution per pixel in the upcoming LAMO orbits? What will it be?
Okay, so that's a great question. We think that we're going to get as close as 30 kilometers to the surface of Ceres, and the resolution scales at about 1.5, times the altitude. So functionally, that means that we can actually sense water ice in the interior of Akator crater, which is one of our targets. So one of the things that we're going to try and do is, we'll be low enough that we'll be able to match up grand data with geologic features such as the interior of Akator and its ejecta blanket. And we'll be looking at a longitudinal swath of Ceres rather than global Ceres.
That's cool. The second question from Diane is, what is the process by which the Murchison polymer was created? Alexander 2017 talks in detail about how sample processing affect the IOM analyses.
Right. So we're talking about the chart about the meteorite analogs, and as I'm not an expert, I think you have to go back to the very earliest chart in the presentation package where the organic materials were being synthesized in the nebula. And so one question that we have, and maybe Simone will address in his talk, is whether or not the organics formed in situ somehow within Ceres, whether they were always there and were simply concentrated in the crust and surface, which is my hypothesis, or if they just splattered onto the surface by an impact. So hopefully we'll find out from Simone.
Okay. Any other questions? Thank you, Tom. We'll go on to the next talk.